right, so we are looking at the second half of section 1.2. Second half of section 1.2. First half of this section, we were looking at math modeling and about how we could take information that they give me in a table or in a chart or in a graph, and how we could use the multiple representations of that information. So we were most often taking the information they gave us in a table, and we were putting that in our calculator and graphing it and doing a regression to try to fit an equation to that information. So we want to pick up today on the top of page 29 with polynomials. Top of page 29, polynomials. Now, I know that we have worked with polynomials extensively before, so just a brief review here of some information about polynomials. They tell me there on page 29 that a function is called a polynomial if, and they give us an example there, the bottom line is that the exponents have to be non-negative integers. Non-negative integers. Now let's think about why that's important. Why would the exponents have to be non-negative? What if they were negative? Why would that matter? Why would they need to be non-negative? Yeah, because if it's a negative exponent, it's going to flip it, right? So in that case, it's not really a polynomial anymore. Then it's a rational function, right? Okay, why would they have to be integers? Why is that important? What are integers? Whole numbers, right? Positive and negative whole numbers. So why do they need to be whole numbers? What if they weren't? Yeah, exactly. If it's not a whole number, if it's a fraction, then remember, if you have a fraction as an exponent, you're talking about a radical. You're talking about a square root or a cube root or something like that. Absolutely. All right, so then we went through, this is the exact same chart that I gave you last year in pre-cal, where I basically went through and just reminded you about the different names of the different polynomials with different degrees and terms. So we could go through and say, for instance, if I have a cubic function, it has a degree of 3, and notice that it always has one less term than degree. So we could say that if it has a degree of 3, then it's going to turn exactly 2 times. We also learned last year about the leading coefficient test, that the leading coefficient tells you how this graph is going to end. So let's say that you had a cubic equation, so it has a degree of 3, and it turns 2 times, and let's say that its leading coefficient was positive. If its leading coefficient is positive, then I know by the leading coefficient test, it's going to end going up. If it has a degree of 3, it's going to turn 2 times, so I could go through then and say, okay, turn once, turn twice, okay, that's the basic shape of that graph. And so that's the power of this table, that it gave us a way to know what the graph was going to look like before we started trying to plot 20 points to figure out what it looked like. So there on page 29, they remind you of some bold print terms: polynomial, degree, coefficients, linear, quadratic, cubic, and then we, of course, expanded that to quartic and quintic. All right, then we get over to the bottom of page 30, and they talk to us about power functions. And it says a function that's in the form of f of x equals x to the a, where a is a constant, is called a power function. And there are several different cases that they give us for these power functions. The first one is when a is equal to n, where n is a positive integer. So that would be something like x to the second, x to the fifth, x to the 25th, x to the 103rd. I mean, any of those would be a power function. So in essence, you're looking at x raised to an exponent, but nothing else coming after that equation. So it's not like x to the third plus 3x squared plus 2x. There's nothing else that comes after it. It's just x to the third, okay? So that's our power function. Now, when I have x to the third, or x to the fifth, or x to the 25th, if it's x raised to an odd exponent, then it's going to look like this second picture over here where we've got, what looks like a cubic function over here where we've got our slide going through. All of them are going to have that same basic shape. So if it were x to the third or x to the 23rd or x to the 103rd, they would all look pretty much the same. Really, the only difference is the higher that exponent is, your graph kind of levels off here in the center more, so you have more of a flat area as you have higher numbers of roots going on there at that center. Similarly, we can do the same thing over here with the even one, where we can say, okay, if I have y to the second or y to the 102nd, it's going to have that same basic shape. The only difference is going to be that we're going to go through, and again, you could just make this a little fatter for each of those different values that you ended up with. So like the difference between x to the second and x to the 22nd and x to the 102nd, that's going to be the difference between those things. All right. The second scenario that they give us is when a is equal to 1 over n, where n is a positive integer. So that would be like 1 over 2 or 1 over 3, something like that. So as we mentioned before, that's going to give us a radical. That's going to give us the square root of x or the cube root of x or something along those lines. And so they graph each of those here for us. They graph the square root of x and they graph the cube root of x for us. So the square root of x we saw last year. That was a graph that we had to know. And then the cube root of x we definitely could generate by making an xy chart, but that's one that we'll utilize enough this year that it would probably be good for you to know what that one looks like as well. The third scenario that they give us over on page 32 is when a is equal to a negative 1. So if a is a negative 1, that's just x to the negative 1 or 1 over x. That's our reciprocal function. And that one, basically, you can see the graph there on the top of page 32, and you can see it there in the bottom of your notes as well, where that one is basically kind of looks like a degenerate hyperbola, where you've got the first piece in the first quadrant, and then you've got your other piece in the third quadrant. All right. Then over on the middle of 32, they talk to us about a rational function. And a rational function is basically a polynomial divided by a polynomial. So we defined at the beginning of the section what a polynomial was. If I have a polynomial divided by a polynomial, then that is a rational function. And again, the root of rational, ratio, something written as a fraction. Then on the bottom of 32, they give us algebraic functions. An algebraic function is just anything that can be constructed by adding, subtracting, multiplying, dividing, and taking the square root. So a function is called an algebraic function if it can be constructed using algebraic operations like addition, subtraction, multiplication, division, and taking roots. So that means that any rational function is automatically going to be an algebraic function, right? Because think about what we said a second ago. A rational function was a polynomial divided by a polynomial, right? Well, you can form a polynomial by adding, subtracting, multiplying, and dividing. And then if you had a polynomial divided by another polynomial, again, that's adding, subtracting, multiplying, and dividing. So every rational function is automatically going to be algebraic. But the reverse of that is not true. Every algebraic function is not automatically going to be rational because of this guy right here. I can have a radical in an algebraic function, but I cannot have that in a rational function. Okay? So when I look at this first example where we have x plus 1 over x minus 1, is that rational? Yeah, because it's a polynomial divided by a polynomial. Is it also algebraic? Yeah, because it can be formed by adding, subtracting, multiplying, and dividing. So it is both rational and algebraic. But I come over here and I look at this next one, x plus 1 over the square root of x minus 1. Is that rational? No, because it's got the square root in it. Is it algebraic? Yes. So we want to be careful of the difference between those two. All right, then they also talk to me about trigonometric functions in the middle of page 33. Now, they're assuming that we did not do Appendix D, and so we have not, covered these graphs extensively, which, of course, we have. So they go through here, and they give you the sine and the cosine curve, and they talk about domain and range and period and coterminals and a lot of those things that we've already talked about. And then over on 34, they give you the tangent. And then they mention that the rest of the graphs, secant, cosecant, and cotangent, are back in Appendix D. All right, on the bottom of 34, we look at exponential functions. Exponential functions. Last year when we graphed an exponential function, we looked at two different types. We looked at the functions that were entirely increasing. So when they are increasing, that's when we have y equals a to the x, where a is a value greater than 1. When the other type was when the entire thing was decreasing, and that was when a was a value between 0 and 1. Both of those, whether it was an increasing exponential or a decreasing exponential, both of them had a y-intercept at positive 1 and a horizontal asymptote at 0. Those were our landmarks. Those were the two keys that we used to sketch those exponential functions. So if we were graphing something like y equals 2 to the x, literally all I would have to do is say, okay, since 2 is a number greater than 1, then I know that's going to be an increasing function. I have two landmarks. I know that I have a horizontal asymptote at 0, and I know I have a y-intercept. So I already know what this piece of the graph looks like. It's going to approach that asymptote. I just need to know over here on this other side, as I come out of that y-intercept, I just need to know how steep to make that other side. So literally we could get away with just plotting 1 or 2 points where I could go through and say, okay, if I put 1 in for x, I'm going to get 2 for y. So I could come over here and say, okay, there's the point 1, 2. That lets me know how steep to make this increasing function, and so I've got the rest of my curve. Okay? So those were our exponential functions. Then we learned that logarithmics were inverses of exponentials. So look at a couple things we know to be true about inverses. For exponential, we had y equals a to the x. What is true about the equations of inverses? How do you find the inverse? You switch x and y. So if you'll notice, if I was looking at a logarithmic, if I had y is equal to the log base a of x, if we switch that from its logarithmic form to its exponential form, that would be x equals a to the y. Look, x equals a to the y equals a to the x. X and y have just switched places. So sure enough, those two are inverses of each other. Something else that we know about inverses is that they reflect in the line y equals x. That's that dotted line that you see there. And so you can see that if I took this point, 0, 1, and I reflected it across that line, I would be at 1, 0. If on the exponential function I had a horizontal asymptote at 0, then on the logarithmic function I have a vertical asymptote at 0. So again, those two landmarks that I use with the exponential, I have landmark equivalents for the logarithmic. So I'm going to have an x-intercept at 1, and I'm going to have a vertical asymptote that I could use to go by. So if I knew that I had an x-intercept at 1 and I had a vertical asymptote at 0 that I was approaching, then again, all I would need to do is just maybe give myself 1 point to know as I come out of that x-intercept how steep to make this other piece of the graph. All right, then on the middle of 35, transcendental functions. Basically, those are functions that are not algebraic. So a transcendental function could be something like a trigonometric function. You can't create a trig function by adding, subtracting, multiplying, dividing, and taking the square root, right? So that's why a trig function would not be algebraic. And so example number 5, they're going to ask me to go through and classify these different types of functions that we've been looking at today. So for example 5, for the first one, we've got f of x is equal to 5 to the x. So what type of function is that we've looked at today? 5 to the x. Yep, that one's exponential. Would that be increasing or decreasing exponential? Increasing, right. So it would have that y-intercept at 1, horizontal asymptote at 0, and it would be increasing. Good. All right, look at the next one. F of x is equal to x to the 5th. What is that one? That is a power function, yes. So make yourself a note. Those two are really easy to confuse. Something like 5 to the x and x to the 5th, they look so much alike. So make yourself a little note to watch out for those. Now, x to the 5th is a power function. That's probably the best description of it. But it is also something else that we looked at today. What else is it? It is a polynomial, and specifically it is a quintic, yes. So power is the specific type of polynomial function that it is. So power is probably the better answer, but it wouldn't be wrong if, you know, you looked in the back of the book and it said that it was also a polynomial, or that it was also a quintic, because that's a polynomial with a degree of 5. All right, how about the next one? 1 plus x over 1 minus the square root of x. What is that? That is algebraic. Is it also rational? No, because remember we said all rational are algebraic, but not all algebraic are rational. Because that one has a radical in it, then it is not. How about D? What is this guy? Yeah, it is just a polynomial, and it's a quartic polynomial, but there's no other way that we could classify that. That's all that there is to that one. Okay, so here is our homework for tonight. On pages 35 to 38, we're doing 1, 3, 4, 13, 19, challenge 11. Now, when you look at the homework and you look at numbers 3 and 4, what they'll have you doing for those is they give you a graph and they ask you to match that graph to its equation. You should not be using a graphing calculator to do that. We should be able to look at all of those graphs that are in numbers 3 and 4 and be able to give the equation for them or match them to their equation without a calculator. And you will be asked to do that on both the quiz and the test on this information. So there is no calculator icon beside those, so that tells us we should not need a calculator to do those. Okay?